Bom, boa tarde a todos, né? Buenas tardes. Temos alguns que estão nos mirando de vários países de América Latina, né? Good afternoon. So today we have the pleasure to have the talk of Professor Samuel Plagarini, directly from Tallinn, Estonia. So as you can see, the slides will be in English and the talk will be presented in English. And next week, we will have the talk of Professor Christina Meinhardt, and the week after, a talk by George Tomfat from the European Space Agency in Graz, Austria. And the week after, a talk by Osvaldo and Marcus that are with Silvaco company. So I give the token to José to do the presentation of Samuel. Thank you very much, Samuel, to accept our invitation to do this talk in a very nice subject.
So first of all, thank you, Samuel, for your talk today. Samuel graduated in the Federal University of Rio Grande do Sul in 2008, if I'm not mistaken. And he's currently a professor at the Tallinn University of Technology in Tallinn, Estonia, where he leads the Center for Hardware Security. He has experience in research appointments at Carnegie Mellon in the US and also at the University of Bristol in the UK. He has a large background in IC design, having tapped out himself, supervised dozens of integrated circuits. His research concentrates on IPs, theft, crypto hardware, circuit obfuscation, and prevention of hardware trojans. So, Samuel, thank you again, and the floor is yours.
Okay, thanks for this nice introduction. Thanks for everyone that's following us on YouTube. I see so many names that I recognize. Really cool. But let's get started. As Jose was saying, I'm now based in Tallinn. I work for the Tallinn University of Technology. We have a nice brand new center for hardware security here. Hardware security in general and in Brazil is not a topic that a lot of people are doing research on. So for many of you, this is perhaps too advanced or perhaps really exciting. We'll see, but I hope you guys enjoyed the slides. Now, a lot of people don't know, have never heard about Estonia, so I want to very quickly say just a few words about the country and the city. Estonia is here, this little dark green country. We're part of the European Union. The capital of Estonia is Tallinn. It's a relatively small city, about 400,000 people live here. But what I find to be really fascinating, if you do a quick Google search, okay, and you look for some headlines, some news about Estonia, this is the type of thing that you're going to see, the type of headlines. People talk about Estonia being the most advanced digital society in the world. And as a homework, if you guys want to Google it and see what we're talking about, what this concept of digital society is, it's quite interesting. Usually people associate the country also with the creation of Skype and TransferWise, two huge names that you probably heard about. I also want to show a few pictures because Tallinn, the city of Tallinn, is really, really old, and we somehow Estonians managed to preserve the old town really, really well. This is a big touristic attraction. This picture I'm showing here is the entrance to the old town. This is called the Viru Gate, and this thing is older than Brazil itself. So, and it's really well preserved. It's really nice. We are also somewhat known for the Christmas market. It's a big attraction. People come from all over Europe to see our Christmas market here in Tallinn, Estonia. Also really, really nice. Okay, but we're here to talk about research. We're here to talk about hardware security. you will notice that the template has already changed a little bit, because most of this work that I'm going to present today, if not 100% of it, was done in the United States. I was a research scientist at Carnegie Mellon University for 4 years, and that's where I started this line of research, and that's what I'm going to show you guys today. Before we move on, I would like to acknowledge some people that work with me, some students and some postdocs that work with me in the US. I also like to acknowledge the funding agencies, DARPA and IARPA, that gave us some really generous funding to do the work I'm going to show next. Okay. Okay, so not everyone is familiar with the funding system in the United States and how things work and how you get money to do your research. Actually, let me turn off my webcam for now so you guys can see the slides slightly bigger. It's quite interesting that the research funds that help me do my work, they all come from military source. They come from the Department of Defense. And I want to sort of explain this background to you so you can understand why this type of research is held in that way in the United States and how things got to where they are right now. If we go back in time, okay, and we're talking about the first transistor, it was invented in the US. If we're talking about where most chips are designed, they're designed in Silicon Valley. That's also in the US. But there was a point in time in the 70s where 37% of all the chips designed in the world, they were procured by the US government. They were the biggest buyer of silicon there was. And most of the reason was the space race, actually. That was the big thing driving out the innovation. With time, things started to change, okay? We had a lot of the memory market shifted to Japan and Korea. We had companies like Fujitsu and Samsung. In the 90s, then we had TSMC enter the scene. It was this new concept of a fab for hire, right? They don't do design, they are only a fab. You send your design, they give you a chip back. So this was a big breakthrough. And what happened was that in the early 2000s, they had these congressional reports already pointing out that the United States would lose access to cutting edge silicon. And this is concerning for them because the most advanced military nation in the world, they definitely want to have access to the best transistors there are. And that's why they fund a lot of research in this area. In this slide, I'm also talking a little bit about some historical perspective. In the 70s and perhaps even in the 80s, having a foundry was relatively simple. It was not that challenging or that costly to have your own foundry. So a lot of companies that were essentially chip design companies, they had also their own foundry. These days, this is impossible. Building a new foundry is like $1 billion effort. And we have seen a lot of shift to Asia. A lot of foundries are shifting to Asia or are well established in Asia. And from the point of view of the American government, this is troubling because they lost access to a trusted foundry, a place they could send some sort of secret design or some designs that were really important for their infrastructure or military or space, whatever critical infrastructure it is. They didn't have, by 2018, they didn't have a place to do that. There was one trusted foundry, but somewhat obsolete and expensive to maintain. So while this is a big, big problem for them, this is an excellent research opportunity because my research goal is to build chips in a place I don't trust, but whatever comes out, of that place I want to trust. So I want to bypass this notion of an untrusted foundry. I still want to have access to the best silicon there is, and I want to make sure that I can trust the silicon when it comes back. So let's talk a little bit about hardware security, and I think I should mention that's a relatively new area. It's not as well established as design, verification, test, or CAT. It's relatively new. And the term security means different things to different people. Some people think hardware security is only crypto. Some people think it's only reverse engineering. So it depends who you ask. In my research in particular, the things that I really care about are these three that I have highlighted here in bold. IP piracy, meaning that I want to be able to fabricate my circuit in an untrusted foundry, and I want to be sure that they cannot copy some of the IPs in my design. I also want to make sure that they will not overproduce my design, make extra copies and sell perhaps in the black market. I want to make sure that no one's going to reverse engineer my chips. And I want to make sure that no one is going to insert malicious logic into my design, or the so-called hardware Trojans. So this is the type of research that I do these days. Now, I like this picture a lot, and I show in all my presentations all the time. If you just look at the package of these two chips, you don't know which one is the fake and which one is the original one. What's interesting is that the chip on the right is a counterfeit, okay? It's a cheap copy of the chip on the left. But the designers that did the fake chip, they actually had to go to a newer technology than the original chip to be able to match the specifications. So they were not really good designers. They had to use a better technology to match the same performance, but they did, and this thing was on the market for a really long time. This is just a simple USB to serial converter. Okay, so this is the first technique I would like to introduce. It's something I spent a lot of time working on. It's called split fabrication. And Carnegie Mellon was really a pioneer in this technique, and I'm very glad that I was able to participate in this research. The idea is relatively simple. You want to fabricate one chip, but in two foundries. You want to use a trusted foundry and an untrusted foundry. You want the untrusted foundry to build the transistors for you and get the best transistors you can out of the untrusted foundry. On top of these transistors that are really fast, you want to still deposit your metals, your interconnect, in a trusted foundry. Perhaps this trusted foundry doesn't have to be as advanced as the untrusted, so you can get kind of the best of both sides. You get to super high performance, but you also get the security, the trust, because you finish the design yourself in a place you trust. If you think of this from the point of view of the untrusted foundry, the one that's only building the transistors, they can't really insert a Trojan in there. They can't insert a malicious logic because they don't know if it is going to be connected to anything. They don't see the interconnect. They don't see any metals. They only see transistors. For them, the chip looks like a sea of transistors, almost a sea of transistors. They also can't really steal your IP because your IP is not complete. Nothing is connected. So that's the big appeal of this technique. This was demonstrated a bunch of times, so it is viable, but there are some problems with this technique, and this is what I'd like to show on the next slide. The first thing is, for designers, okay, you need a PDK that is hybrid PDK. You need a PDK that has the transistors from the untrusted foundry, but has the metals from the trusted foundry. And no one is going to give you that PDK. You have to develop yourself. I have developed a bunch of those for my experiments and for my research. It's not something pleasant, I can tell you that. Really not pleasant. Perhaps if you have an enemy of someone you don't like that much, you can give them this job. It's not nice. There's also a problem with yield, okay? Let's say you fabricate this chip using 2 foundries. The chips come back, they don't work, okay? They don't pass testing. Who are you going to blame? Who dropped the ball? Who gave you low yield? Was it the untrusted foundry or the trusted foundry? You don't know. You can't blame anymore. Another concern was alignment. This was addressed really early on. And the concern was that it would be hard to deposit metals on top of a wafer that another foundry produced. This is actually quite simple. There are very simple techniques to do alignment. This is something that is done every day in a foundry. When you send a chip for fabrication, your wafer inside the foundry travels from machinery to machinery, from step to step. So alignment is really trivial to solve. But what I like to identify as the actual, let's say the bottleneck, or the one thing that killed this technique, is a logistical problem. You can't find foundries that are willing to do this. Foundries don't want to give you unfinished wafers. They are afraid that maybe this will reveal some secrets of their technology or something similar. It's just not their core business model. So good luck trying to find, a foundry willing to do this. Good luck trying to convince Intel, IBM, TSMC, GlobalFoundries to do this for you. They really don't want to. Okay, so what is the alternative? I like this technique really a lot. I believe the technique works. It really hides the design from the foundry, but I can't get it to work because of logistical problems. So what we developed is a new technique. Instead of split fabrication, we call this split chip methodology. The idea is kind of the same. You still have a trusted side and an untrusted side. But instead of doing the sort of horizontal cut in the metal stack, let's do a vertical cut. Let's build 2 chips. Let's do a trusted chip and an untrusted chip. I can get all the performance I want in the untrusted chip, all the high density that I need for my designs. I can get it on the untrusted chip. And perhaps some of the logic that's not that high demanding, I can put on the trusted chip. If you do this very carefully for some designs, you might find that there is no performance loss. Some designs might allow you to make a very good split that will allow you to lose 0 performance. Of course, this is not the general case, but for some designs, it is. Another thing that is interesting to highlight here is that you have this interface between the chips. This interface was inside the original chip, right? If you produce this as one single chip, it was internal. It was not exposed. The pins were not there. They were all internal. They were not visible from the outside. But now, when you have 2 chips, they need to have some form of communication naturally. And now we have to think about this interface, how to protect this interface, how to make this interface design-friendly, verification-friendly, and also high throughput, high bandwidth. The characteristics that I'm looking for, okay, for this technique to be successful, for split chip to be successful, the trusted chip probably do it in a legacy technology node, so doesn't have to be the state of the art, doesn't have to be 5 nanometer FinFET. No, it can be something older. But what matters is this has to be done in a domestic and trusted foundry. It has to be, otherwise the technique makes no sense. On the other side, on the untrusted chip, then I will use an offshore foundry, untrusted, and I will get the best silicon I can buy. And this is a good fit for the high performance I'm looking for and for high density. From the point of view of functionality, what I'm looking for the trusted chip is to be more control-oriented. This is going to be the brain of the system. On the untrusted side, it's going to be more data-oriented. It's going to do more processing, data crunching. This is what I want to have on the untrusted chip. And this is the research that we did. And we actually fabricated 3 demonstration vehicles with this split chip concept. And in the next few slides, I'm going to talk about these demonstrations that we did in silicon. The first demonstration we did is this design I'm showing you here. This is a GPS correlator design. The GPS correlators, they kind of get the GPS signal from the satellites, and they try to identify what satellite you're talking to. It's not really that complex, but the idea is the more correlators you put in a design, the faster you lock the GPS signal. So you want these correlators to be numerous, and you want them to be fast. So we created this sort of master-slave architecture, where on the left, I have all these correlators on the untrusted chip. They're running at 2 gigahertz, really, really fast. And they're kind of really doing all this data crunching to figure out what satellites I'm currently seeing, what GPS signals I'm receiving. On the other side, on the trusted side, I don't have to do the heavy data crunching. I can maybe do just some tracking. I know what satellites I was talking to maybe a minute ago. I can assume I'll probably keep talking to them. And you can do the tracking operation of the GPS, actually plot where you are on the globe on the trusted side. This is more or less the idea of this design. And I call this a master-slave architecture because the trusted side kind of dumps a lot of information for the untrusted side to compute on, and only gets a really nice result in the end that's only 10 bits. So yeah, you deliver a lot and you get 10 bits back saying, yeah, I got it. So the communication here is pretty simple. On top of split chip, in this demonstration, we also added some other hardware security techniques. We added some dummy logic, some key logic, and some layout obfuscation. So dummy logic, it's a very simple concept. This design originally was supposed to have 1,000 correlators. So we went in and we added another 20 or so correlators. They look like they're functional. It looks like they're connected to all the buses and they talk to all the other correlators, but they really don't. They're never activated. So they're dummy. They're just sitting there to make someone that is trying to reverse engineer this design, make them a little bit more confused about what this design is. For the other 2 concepts, key logic and layout obfuscation, I have 1 slide for each. So let's talk a little bit about key logic. Now, key logic is really, really popular in the hardware security community. This is not something I created. There are probably hundreds of variations of this concept already. The most simple one is the one I'm showing in this slide here. On the left, I have the original circuit that I'm trying to protect. And on the right, I have the modified circuit. The idea is you insert this XOR and XNOR gates that were not part of the original design, connect them to a NAT that was originally part of the design, and the other input of the XOR gate, you add a key input that was not part of the original design. When you fabricate this chip, you don't tell the foundry what values of K1 and K2 are meant to be used. You do this post-fabrication. You do a post-programming step where you actually set the keys that you want. The idea is, if the foundry tries to copy your IP, or even if they try to copy the entire chip, they try to steal it. They don't know what values to put in the keys. They don't know how to do this post-programming part. And this is why this technique is effective. You leave some of the secret in there. You don't you give all the netlist to the foundry. They have all the layout, everything is complete, but they don't know what inputs to apply to it. This is the concept of key logic, and there are many, many variants of this. In terms of layout obfuscation, what we did is something that I call a lightweight layout obfuscation. For those of you that are familiar with IC design, when we are doing our floor plan, it's very common that we have these big boxes here where we sort of try to organize our floor plan to make it easy to place, easy to route, okay? In this particular design, I had these 1,000 correlators. I could just copy and paste the same correlator 1,000 times, and that will be okay. And this would be very hierarchical, but from a design point of view, that would be okay. From a reverse engineering point of view, someone looking at my layout will very quickly realize there are 1,000 units. I don't necessarily know units of what, but there are 1,000 units that are repeated. He only has to understand what one of those units is, and then he'll figure out the other 1,000. So what we did is, instead of doing a hierarchical floor plan, we did like a flat floor plan. So we don't have these nice boundaries between correlator modules. Instead, we took some specific cells, we used them as seeds for placement. If you're familiar with placement in CAD VLSI, you can kind of fix the position of some cells and let the other cells arrange themselves around those that are fixed. So that's what we did. If you do this in a clever way, actually there is very little overhead. And the layout that you get in the end can be unique. Instead of having 1,000 repeated small modules, I can have 1,000 modules that never repeat. The layout of each module is slightly different from the one before. If you look at these 1,000 correlators from an external point of view, the aggregate of all these correlators looks like a huge piece of logic, and you don't really know what it does. So this is kind of a lightweight obfuscation, because if you put the netlist together, you can probably still figure out that there are units in there that are repeated, but from a layout point of view, you can't. Okay. Here in this slide, I'm showing the first chip we fabricated. This is the chip with the 1,000 GPS correlators I was talking about. On the left, we have the final layout. On the right, we have the unpackaged die with a 1-cent coin there for reference. One of the things we realized is that for this design, it was really easy to find where to split the hierarchy between, trusted and untrusted because of the application. The application really made our lives easy or easier. But this is not the general case. Another thing is we had, in this first demonstration, we didn't worry much about communication between chips. We could have consider some form of encryption, but on this first demonstration, there is no encryption. So all signals that travel from trusted and untrusted, they are in plain text. They are not encrypted in any way. Okay, but we did the first demonstration. It worked. So we moved on. We wanted to do a bigger demonstration, and this is what I'm calling demonstration number 2 here. Instead of 1,000 correlators in this design, we had 300,000. This chip is 5 millimeters by 5 millimeters in 16 nanometer technology. It has about 20 million standard cells. Some areas have really high density. If you see these red dots here, these are areas that have over 70% density. In newer technologies, I can tell you 70% is not easy to route. You're going to have nightmares. You're not going to sleep at night trying to route this design. And yeah, but we did it. If you look at this floor plan here on the left, you can see there are these gaps. You can see some areas that don't have a lot of routing. It's because the floor plan is organized in a 3x3 matrix. And I'm going to tell you why this is a 3x3 matrix. We had this notion of channels. We had to break. There's a big return. Zain, if you are on this call, maybe mute your microphone, okay? So we split this design into 9 channels. They're kind of equivalent, but the problem we ran into in this design was actually power distribution. We could make the correlators work in the range of 2 gigahertz, but the problem is we could not supply enough VDD, enough current, for all of the correlators to work at 2.4 gigahertz. So one of the possible configurations for this chip to work is just channel 0 works at 2.4 gigahertz and the others cannot work. Another possible configuration is you have 2 channels enabled, channel 0 and channel 1, each working at 1.2 giga. This is fine, we can still supply enough power. Next, you can have 4 channels working at 600 mega, and finally you can have all channels working at 300 mega. This is possible, we can supply this configuration with enough current. There's a last configuration. This is only for test purposes. We had the chip working at 1 mega just for bring up and debug, essentially. If you're familiar with IC design and if you're accounting, you might be wondering if this was a lot of work, and I can assure you it was. This number of clock domains is a nightmare to manage, and this thing took a really long time for us to achieve, but in the end we did, and the chip actually came back and it works. In this image, I'm showing our test bed setup or test bench setup. When the chips came back, we actually put them on a PCB, and we were able to test them and make sure that the split chip concept actually is functional and it's validated. In this yellow area here, we have a socket. You can't really see the chip, but the chip is there under the socket. This is the chip with 1,000 correlators we have in there, and this is acting as the untrusted IC. On the back, you can see there's another board. That's actually a test equipment. This is a NIDAC equipment, if you're familiar with that. And this guy is acting as the trusted IC. He is driving the untrusted IC. He is delivering tasks. He's delivering data for the untrusted IC to compute, and the untrusted IC gives the GPS correlation result back. You can also see here in the picture some key bits. This is related to key logic that I was talking about. So in this demonstration, it's actually the trusted IC that holds the keys, and it sends the keys to the untrusted design to make sure that it works as expected. So those XORs and XNORs that we have in there, we drive them with the right values to make sure that the chip maintains the intended functionality. These bits are not shared with the foundry. So if someone was trying to steal this design, they will not know what bits to put in there to make this thing behave as intended. Okay, one of the interesting things we learned from this experiment. First, and most important probably, for this design, we got 0 performance loss. And this is great, but it's specific to this design, to the way it is naturally conceived. It lends itself really well to be partitioned into a heavy computation unit and a very lightweight control unit. But other things we figured out during this experiment is that there are some really complex trade-offs between bandwidth, latency, and the security you get. Some of these challenges are related to chip-to-chip communication that's much, much slower than communication that is internal to the chip naturally. The question that we had next was, okay, can we automate this process? Can we find some sort of tool? Can we develop a tool that will tell me for any specific design how to partition it? And this is what we did. So we developed this tool. It's a CAD tool that does the split chip analysis for you. One of the reasons we need a tool to do this for us is because the technologies can be very different in nature, right? The untrusted IC is probably going to be a very brand new technology, very fast, very performant, and the trusted IC probably not as much. So the tool has to understand that technologies are different and the overhead of moving a certain module to one side or to the other side is different. What I'm showing here on the left is what a single chip implementation would look like. And on the right, I'm showing what the split chip implementation would look like. These modules, drawn in red, okay? These are considered critical IP. They are the ones that really have the secrets you want to hide from the foundry, okay? Blocks like G and B. Ideally, I would like for my critical IP to be on the trusted side, just like G. However, sometimes there's IP that is critical, but is also so important for the performance of the entire system that I have to put it in the untrusted IC so I can leverage the use of the fast transistors of the untrusted IC. If this is the case, I need to think of some way to obfuscate my design. This is an IP that I really care about. It's going to be in the untrusted IC, and I want to obfuscate from the untrusted foundry. There are many, many solutions for this. I've talked about key logic before. Here in this slide, I'm showing you some of the existing techniques for doing this. These are all variants of key logic. I would like to highlight some of the overheads here. These are not good overheads. We have very commonly overheads of 100% in area, 100% in power, and also sometimes 100% in timing. So there's still a lot of ongoing work in these techniques, but the important message here is that they do exist, and to some extent we believe they work, and we can send a chip for fabrication in an untrusted foundry, and there are huge overheads, but you can still get away with some of this. You cannot apply this to your entire chip, at least that's my belief. But to some portions of the chip, if necessary, you can. So essentially the knowledge that I had in the previous slide, this notion of which techniques are good and what are their overheads, we sort of encoded this into our split chip tool. In the next few slides, I want to guide you through a study case. And this is using the common evaluation platform developed by MIT. This diagram here on the left is what the common evaluation platform is. It's essentially representative SoC. It has your typical cores, it has memory, it has some crypto, and also has some accelerators. It does some specific I/O, very typical SoC. And what we did is we submitted this design to our split chip partitioning tool to try to figure out what's the best way to split this design. The way the tool works internally, it tries to do this vulnerability optimization. So first, I would like to explain what's on the right side of the slide. This is the notion of criticality. For each module that is part of the system, we kind of expect the user to give us some scores for criticality. Okay, this is essentially how much the user cares about that module. If he doesn't care, then that's fine. If he cares a lot, then he put a high number like this. This in particular here is the GPS example. On the other side, we have something called the exposure. So depending on what configuration the module is going to be, if it is going to be on the trusted side, the exposure is low. If it is going to be on the untrusted side, the exposure is going to be high. And there are all other options in between for the obfuscation options, configurations. What I'm trying to do is I get the product of these two, exposure and criticality, and I try to minimize this for the entire chip. This is what the graphical interface of the tool looks like. I will go through this relatively quickly. If you don't understand, please check the slides later. But the way it works is like this. In the initial run, what we call run 0, you put all the modules of your system on the untrusted IC. And you calculate what the vulnerability is, the vulnerability that you get based on the criticality and exposure values that you have for your system. Now, step by step, you start to relax some of the constraints. You allow the system maybe to burn a little bit more power, maybe to run a little bit slower, and the tool is able to reason and figure out that some modules can now be shifted to the trusted IC. And this is what is happening here in this diagram. So blocks that are in blue, they're now passed to the trusted IC, and you can see that the vulnerability score that I calculated before goes down from 4.8 to 2.3. Because, of course, I trust what I put in the trusted IC. There are more steps to this, and I'm going relatively quick here. I can also apply obfuscation. That's why you have some different colors here. You have orange, green, and red, because now I have variants of obfuscation solutions. And my vulnerability keeps going down the moment I apply these obfuscation techniques to my system. Finally, in this specific case, at the very end, we saw that we could do some small tweaks, just increase maybe a clock frequency by, a clock period by 1%, and it would be enough to make a small change in the vulnerability. And that's what we did in this last step, and we get a final vulnerability score of 1.6. This is where the tool ends, and now the user has to decide if this is sufficient or if he needs to keep going. Another thing we did, this is kind of unique to split chip. If you have this interface that I talked about before between two chips, this interface didn't exist initially. You might be thinking about protecting this interface. The most obvious answer to how to protect this is crypto. Okay, you want to encrypt the data that goes in and out of these chips. We came up with a system that does a pairing of trusted and untrusted ICs using SRAMs as signatures, as physically unclonable functions. The way it works is you can program the trusted IC so that it would only bind to a unique untrusted IC. So an adversary cannot just replace any of the chips in this pair by something else and try to figure out what the system does. Okay, so we are approaching the end of my presentation here. And the title of this presentation was, can we build a trustworthy billion transistor chip? And at this point, I would like to answer this question to you the answer might be disappointing, but it is what it is. Yes, we can build a trustworthy-ish billion transistor chip. The problem lies in measuring trust. I showed you guys this table before, okay? And I showed you these numbers for exposure, for what I believe are representative numbers for exposure of a trusted IC, untrusted IC, and untrusted with different levels of obfuscation. But I have to be critical here and say this is my interpretation of the state of the art. Other people have different interpretation, but most importantly, this is a widespread problem for the hardware security community. Is the lack of metrics, or lack of metrics that people actually believe in, that I can use to measure the efficiency of my technique versus the efficiency of your technique. So yeah, the best answer I can give you is the chip I design is kind of trustworthy-ish. Okay, I'm going to end my presentation here. I see that we have some questions already. I had 2 more slides. It's not really relevant. We're going to skip right to the end. And yeah, that's all I had to present today. Thanks everyone, and now we're going to open for questions.
Samuel, thank you for your talk. Let me ask you to turn on your camera again.
It should be on, or about to turn on.
Yeah, I can see it here. We have a small delay to the YouTube channel, so I'm getting some questions from YouTube. The first one, I don't think it's a question, but more like a comment, saying that from Vitor, he says that spectral graph theory could be useful in this partitioning.
I can tell you there's a guy that did a whole PhD on this, or he's doing a whole PhD on this. We tried a lot of different approaches, some machine learning, we tried some bounding algorithms. Actually, the problem is not that hard because the number of modules that you have in an IC, we're not talking about 1 million modules, we're talking about hundreds. Perhaps if you have a huge SoC, 1,000. And for some of these SoCs, you can even do exhaustive search. You can exercise every single combination of modules in trusted and untrusted side. So yeah, I believe there's a lot of techniques out there that can help you do this maybe in a fraction of a second, but exhaustive is not impossible. We have actually done it.
Okay, the second question is from Clovis, and he asks, how much higher is the price of the final product?
Okay, so this is a very interesting question. Let me first say that if your #1 concern is security, price doesn't matter, right? Let me also say that military products, space products, in general, they are really low volume. You know, this is not your Intel processor that they're going to sell millions and millions of copies, and the price of design is going to be divided by the number of copies. In military products, we're talking maybe about thousands of chips, thousands of chips that you will produce. So cost doesn't really matter. Maybe design cost, you know, salaries that you had to pay to these guys that spent maybe a year and a half working on the design, it's actually what matters.
Okay. I also have 2 questions. The first one is, usually in IC design, you have a design space where you pay some kind of a price for something, right? Usually area times performance or something like this. So in this case, one axis would be security and the other one is some kind of a cost, right? Either in performance or area. So just to be sure, for military applications, for example, and for space application, there is no design space. It's basically get me the most security you can get. Or do you actually have some kind of constraints in area and performance?
Not in area. Area really doesn't matter these days. Performance for sure. If you reach a split solution that has a low throughput, maybe it killed your entire application if it doesn't run as fast as it should. Power depends. Power really depends if we're talking about battery operated or not. I would say of those three you mentioned, performance is usually the number one, or security is number one, performance is number two. I think that's a very reasonable assessment for this type of application, very specific case of military applications. This is not your typical Intel processor. This is not your NVIDIA GPU, right? This is a very different beast.
And my second question is, well, this is mainly targeted at military applications, of course. But your split chip architecture, you mentioned early in your slides that the design flow is kind of broken and foundries are not very glad to design half of a chip only, being in the metals only and the transistors. So my question is, if we move to more end user, this secure hardware design, let's say, if we are going to use this security flow for a normal processor, let's say a RISC processor, for example, to use in your microwave, right? Like simple application. Could you see that mass production could lead to foundries being able or being more open to designing the split chip approach?
That's a very good question. So let's talk about motivation. What is the core business of a foundry? Is to sell chips for high amounts of money. What drives the founder business these days are cell phones and chips that go into cars, essentially. This is what keeps the IC industry running. Perhaps in the near future, we will have some sort of new Spectre meltdown crisis where we will find that there was a Trojan in the microcontroller of some electronics in your car. I believe that if that happens, then we will see a significant shift in consumer electronics towards hardware security. Right now, the concern is just not there. Really, it's so secondary. We want to make the chips as cheap as possible, as high performance as possible, and we don't even care about things like aging sometimes, right? We're talking about obsolescence, programmed. They want their chips to stop working 2 years from now. Yeah, a lot of things have to happen for us to get to a point where, the chipset in your new Samsung cell phone is going to be a split chip design. We're not there yet.
And also for our final question, on the subject of aging and also military and space applications, Monica asks if there is any study on how faults affect these chips with trust and untrust approach. I don't think we publish much on the test side of things, but we definitely analyzed to make sure we were not creating scenarios of really low yield. Okay. Fernando is also asking how the metrics of vulnerability and criticality are related to the developing of new ways to attach the chip.
We made this really flexible in our tool. The user defines the criticality and the exposure based on, so criticality is based on his design, right? The user knows exactly what's in his design. And by user, I mean, this is the IC designer that's using our tool. This is what I call the user. He knows every single module that's in the system. He knows what is critical and what is just your vanilla microprocessor that no one cares. So you can define the criticality any way you want. For exposure, then you have to start thinking about what threats do you really care about. If you are thinking about engineering by the untrusted foundry, right? They want to copy your IP. Make sure you pick the numbers that would make the tool put the least amount of logic on the untrusted side, right? This is logical. However, if your threat model is different, if you're worried about reverse engineering in the field after both chips have been fabricated, you already lost this battle. You can't win. So it doesn't really matter if things go into the trusted or untrusted side. Adversaries can reverse engineer the layout of both with a certain ease. So it's all about your system, and it's all about defining who's the adversary and what are the capabilities of the adversary. You play with the numbers, the tool is there. The tool will take any numbers you give it, and it accepts any sort of scenario you think it's adequate for your application.
Okay, thank you. We are reaching the end of our time. So I would like to thank you so much. It's very interesting to hear about hardware attacks. We're used to hearing about software piracy, software theft, but hardware theft, you don't see it every day. So thank you so much for your great presentation and all your answers and comments. And just to finish, before giving the floor back to Reis, I would just like to ask you, where can we find your articles, the referenced papers you just mentioned, and also you mentioned previously that you're looking for students to go to Estonia and work with you. So maybe just summarize some open positions and what you're looking for, just like some end comments, and then I would already like to thank you so much for your presentation.
Okay, in terms of publications, a lot of the stuff I showed you guys today is unpublished. And especially that demonstration number 3, I'll never be able to publish that. Unfortunately, the biggest chip of my career, I'll never be able to publish. Hey, how cool. But that's the nature of the game. Some of the things will go unpublished. In a more general sense, journals that usually have good research in hardware security are Transactions on CAD, and the conferences that usually have good stuff in hardware security are DAC, DATE, HOST, and ICCAD. I think that's a really good summary of where to find good references. I believe this presentation will be available on YouTube later, so maybe we can put in the comments some of the references that I have used in this text, in this presentation.
Okay, so thank you again, Samuel. We have around, I think, 90 viewers on YouTube or something like that. I would just like to kindly ask you to consider subscribing to our YouTube channel so that you can know when we are going live. We have a new talk next week on Friday. And Reis, if you could please talk a little bit about our schedule for the next week.
So thank you, José, to chair this session. Thank you, Samuel, to give a very interesting talk. So I saw here in YouTube that we reach in a moment 97 participants, more the participants in the MConf. So we had more than 110 participants. So very nice numbers. So we had participants also from other countries from Latin America, mainly Colombia, also participants from USA, from France, from Algeria. So nice. So
from Estonia, I see my students here.
Estonia also, yes, for sure.
Yeah.
So thank you very much, all you again. Thank you, Samuel. I don't like to know if you want to say something more.
I just want to thank all of you guys for the invitation, for the organizing this very nice setup, and you know, everything comes around, right? I was a student taking this class maybe 10 years ago, and now I'm here giving a talk. So it was really cool. Thanks for the invitation. Yeah, and I'm happy to do it again anytime soon.
So thank you very much to everybody. Thank you again to Samuel for this very nice talk, and thanks to all attendees. And I hope to see you all next week in this same YouTube channel of CAS Society. Thank you very much. Bye-bye, and have a nice weekend.